In 1905, while trying to understand light and motion, a 26-year-old patent clerk named Albert Einstein, a man who spent his days reviewing other people's inventions, wrote an equation small enough to fit on a postage stamp. E equals mc squared. He was studying light, not weapons. He did not know how to split an atom, and he could not have imagined an atomic bomb. But his equation revealed something astonishing. Matter itself contains an almost unimaginable amount of energy. Yet only 40 years later, a fraction of that energy would be released over Hiroshima and Nagasaki, devastating both cities and changing warfare forever. More than a century later, in 2026, the possibility of Iran developing a nuclear weapon remains one of the central issues in its conflict with the United States. So how did an innocent idea about light and motion become connected to the most destructive weapon ever created? So, in the next 15 minutes, I will tell you, in simple language, the story of E equals mc squared and how it changed the world forever. Before Einstein, scientists generally treated mass and energy as two completely separate things. Mass was the amount of matter in an object. Energy was what made something move, heat up, or produce light. But while studying light and motion, Einstein discovered that this separation was not entirely correct. He imagined an object releasing energy in the form of light. His calculations showed that when the object lost energy, it also became slightly lighter. Einstein expressed this connection through a simple equation. E equals mc squared. Here, E is the energy, m is mass, and c is the speed of light, approximately 300,000 kilometers per second, fast enough to circle the Earth 7 times in a single second. And because the speed of light is squared, the number becomes enormous. If just 1 gram of matter, about the weight of a paperclip, could be converted completely into energy, it would release approximately the same energy as 21,000 tons of TNT. Einstein had not invented a weapon. He had simply uncovered one of nature's fundamental rules. A tiny amount of mass could represent an extraordinary amount of energy. But there was still one major question. How could anyone actually release that energy? The first major clue would arrive 27 years later. 27 years after Einstein published his equation, in 1932, 2 scientists at Cambridge University decided to look inside the atom. To understand their experiment, remember the atom's basic structure. At its center is a nucleus containing protons and neutrons. Electrons occupy the space surrounding the nucleus. John Cockcroft and Ernest Walton built a machine that could accelerate free protons to extremely high speeds. They aimed these protons at lithium. When one of the protons entered a lithium nucleus, something remarkable happened. The combined nucleus split into 2 helium nuclei, which flew apart at tremendous speed. But here was the puzzle. The 2 helium nuclei carried much more energy than the incoming proton had provided. Where had that additional energy come from? When scientists compared the mass before and after the reaction, they discovered that the 2 helium nuclei were slightly lighter than the original lithium nucleus and proton combined. The missing mass had become energy, exactly as Einstein's equation predicted. For the first time, humans had deliberately triggered a nuclear reaction and observed measurable energy emerging from mass. But this was not yet a chain reaction. Every lithium nucleus required another accelerated proton from the machine to be converted into 2 helium nuclei. The reaction could not continue by itself. Then, only 1 year later, in 1933, a Hungarian-born physicist named Szilard began considering a frightening possibility. What if one nuclear reaction could automatically trigger several more? Meanwhile, Adolf Hitler had come to power in Germany, forcing many Jewish scientists to leave the country. Szilard was among them. He left Berlin and moved to London, where his idea of a self-sustaining nuclear reaction began to take shape. Scientists had recently discovered the neutron, a particle inside the atomic nucleus that carries no electrical charge. A positively charged proton gets pushed away by the positive charge of a nucleus, like forcing two magnets together the wrong way. But a neutron feels no push at all. It could slip inside much more easily. Szilard imagined that if one neutron entered an atom, it might cause that atom to release two more neutrons. Those two neutrons could trigger two more reactions, releasing even more neutrons. The number of reactions would continue multiplying. Szilard had imagined the nuclear chain reaction. Unlike the lithium experiment, it would not require a machine to provide a new particle for every reaction. Once started, the reaction could grow rapidly by itself and release an enormous amount of energy. The possibility disturbed Szilard so deeply that he patented the idea, and later arranged for the British government to keep it secret. However, one crucial piece was still missing. Szilard could describe how a chain reaction might work, but he did not know of any element capable of producing one. For 5 years, his idea remained only a frightening possibility. Then, in December 1938, scientists inside Nazi Germany performed an experiment with uranium and found the missing piece. In December 1938, at the Kaiser Wilhelm Institute in Berlin, chemists Otto Hahn and Fritz Strassmann bombarded uranium atoms with neutrons. They expected the uranium to absorb a neutron and become a slightly heavier element. Instead, their experiment produced barium, an element approximately half the size of uranium. The result seemed impossible. At that time, scientists did not believe that such a large atomic nucleus could simply break in half. Unable to explain what they had observed, Hahn sent the results to his former colleague, Lise Meitner. Meitner was a Jewish physicist who had been forced to flee Nazi Germany earlier that year. Now living in Sweden, she studied the results with her nephew, physicist Otto Frisch. During a winter walk, they finally understood what had happened. The uranium had not simply changed into barium. Barium was one of the smaller nuclei created when the much larger uranium nucleus broke apart. When a neutron enters the nucleus of uranium-235, it makes the nucleus unstable. The uranium nucleus then splits into two smaller nuclei and releases 2 or 3 free neutrons. When scientists compared the mass before and after the split, they found that the products were slightly lighter than the original uranium nucleus and the neutron that entered it. That tiny amount of missing mass had become energy, exactly as Einstein's equation predicted. Most of this energy is carried by the two newly formed nuclei, which shoot apart at tremendous speed. The released neutrons can then enter other uranium-235 nuclei and make them split. Those reactions release more energy and more neutrons, which split even more nuclei. When this happens across countless uranium atoms almost simultaneously, it creates extreme heat and a devastating blast wave. Otto Frisch gave this splitting process a name: nuclear fission. This was the self-sustaining chain reaction Leo Szilard had imagined 5 years earlier. The missing piece had finally been found, and it was discovered just as Europe was moving towards war. By early 1939, news of nuclear fission had spread through the scientific world. Leo Szilard immediately understood what it meant. Uranium could release energy and additional neutrons at the same time. The chain reaction he had imagined was now physically possible. But the discovery had been made in Germany. During the 1930s, Adolf Hitler had rebuilt Germany's military and begun expanding across Europe. Germany annexed Austria in 1938 and occupied Czechoslovakia in March 1939. Scientists who had escaped the Nazi regime began to fear that Germany might use nuclear fission to build an atomic bomb. Szilard wanted to warn the United States, but he was still a relatively unknown refugee. He needed someone whose name the American president would recognize. That person was Albert Einstein. In the summer of 1939, Szilard and fellow physicist Eugene Wigner visited Einstein and explained how a uranium chain reaction might produce an extremely powerful weapon. Einstein was a committed pacifist, but the possibility that Hitler might obtain such a weapon first deeply concerned him. On August 2, 1939, Einstein signed a letter addressed to U.S. President Franklin Roosevelt. The letter warned that uranium could be used to create extraordinarily powerful bombs and urged the United States to support nuclear research. Less than 1 month later, on September 1, 1939, Germany invaded Poland. Britain and France declared war on Germany 2 days later. World War II had begun in Europe. When Einstein's letter finally reached Roosevelt in October, the warning could no longer be treated as a distant scientific possibility. The United States began investigating whether an atomic bomb could actually be built. The race for the bomb had begun. At first, American research moved slowly. Scientists still had to prove that a large-scale chain reaction was possible, and that a bomb could actually be built. Meanwhile, the war continued to spread. Germany conquered much of Western Europe and invaded the Soviet Union. In Asia, Japan continued expanding across China and the Pacific. Then, on December 7, 1941, Japan attacked the American naval base at Pearl Harbor. The United States officially entered World War II. The atomic bomb research suddenly became far more urgent. In 1942, the U.S. Army created a secret program called the Manhattan Project. It was given that name simply because its original Army office was based in Manhattan, New York. The project was placed under General Leslie Groves, while physicist J. Robert Oppenheimer was chosen to lead the scientific work. The scale was extraordinary. Secret facilities were built across the United States. Oak Ridge in Tennessee worked on separating uranium-235 from natural uranium. Hanford in Washington produced a new fissile material called plutonium. Los Alamos in New Mexico brought scientists together to design and build the bombs. More than 100,000 people eventually worked on the project, but most were never told its true purpose. Then, on December 2, 1942, beneath the stands of an old football stadium in Chicago, a team led by Enrico Fermi achieved the world's first controlled, self-sustaining nuclear chain reaction. Leo Szilard was there, watching the idea he had imagined 9 years earlier finally become reality. But Albert Einstein was not involved. Although his equation explained the energy and his letter had helped alert Roosevelt, American authorities considered Einstein a security risk because of his political views, and excluded him from the project. The chain reaction had now been proven. The next challenge was to turn it into a weapon before Germany could do the same. By 1945, the Manhattan Project had developed 2 different types of atomic bomb, one using uranium and another using plutonium. But the war had changed. The bomb had originally been developed out of fear that Hitler might build one first. However, Germany surrendered on May 8, 1945, before the atomic bomb was ready. The Allies would later discover that Germany's nuclear program had never come close to producing a bomb. But the war against Japan continued. Before using the new weapon, the scientists needed to know whether it would actually work. On July 16, 1945, they tested a plutonium bomb in the New Mexico desert. The test was given the code name Trinity. At 5:29 in the morning, the first atomic explosion in history illuminated the desert with a flash brighter than daylight. A fireball rose into the sky, followed by a massive mushroom cloud and a shock wave that traveled across the desert. The explosion released energy equivalent to approximately 21,000 tons of TNT. The energy represented by roughly 1 gram of mass, the weight of a paperclip. The bomb worked, and less than 3 weeks later, an atomic bomb would be dropped on a city. Fighting continued across the Pacific. On July 26, 1945, the United States, Britain, and China issued the Potsdam Declaration, calling for Japan's unconditional surrender. Japan did not accept the declaration. On the morning of August 6, 1945, an American bomber named Enola Gay flew over the Japanese city of Hiroshima. It dropped a uranium-based atomic bomb called Little Boy. The bomb exploded above the city, creating an enormous fireball, intense heat, and a powerful blast wave. Hiroshima was devastated. Tens of thousands of people died immediately, and many more died later from burns, injuries, and radiation exposure. 3 days later, on August 9th, the United States dropped a second atomic bomb over Nagasaki. This bomb was called Fat Man. It used plutonium and was based on the same general design tested at Trinity. Nagasaki was also devastated, with tens of thousands of people killed. Between the two bombings, the Soviet Union declared war on Japan and began attacking Japanese forces in Manchuria. These events occurred within only a few days. On August 15, 1945, Emperor Hirohito announced that Japan would accept the Allied surrender terms. Japan formally signed the surrender documents aboard the USS Missouri on September 2, 1945. World War II was over. But one fact was undeniable. A scientific equation written 40 years earlier had become connected to a weapon capable of destroying an entire city. But the atomic age had only just begun. In the decades that followed, nuclear weapons reshaped global power, military alliances, and international conflicts. Even in 2026, as the United States and Iran remain in conflict, the possibility of Iran developing a nuclear weapon remains one of the central issues. Even though Iran is not confirmed to possess one, Einstein's equation did not build the atomic bomb. It revealed the enormous energy hidden within matter. Human beings discovered how to release that energy, and the world has lived with the consequences ever since. If you found this story worth your time, a like and a share helps more than you might think. And comment below, what should I explain next? Thank you for watching.